No. I had it about her. Yay. It's true.
Alrighty. Okay, sorry to get it started a little late. But welcome. Short, small amount of people today, but that's okay because then you can ask your questions. What would we like to see today? What would we like to go over?
What you did in class today?
What you did in class today? Yep, absolutely.
And today too.
Do you want to like just kind of start at Monday and move into today? Or do you want to start at today and go back to Monday?
Maybe Monday.
Monday into today? Absolutely. Okay, so thermochemistry is probably going to be one of the toughest chapters you cover this semester, between that and then like acids and bases, I would say. When you think about thermochem, it does take a lot of time to kind of understand what's happening with like the system and the surroundings and how you have to orient yourself when you think about it. But the more you practice, the more problems you do with this, the easier it will get. So I promise it does get a little bit better. But no, even us still have a little bit of issues every once in a while. I know that this is always one that I have to like review the information before I teach it and stuff. Okay, so when we talk about thermodynamics, what do you remember from class? What did we cover? Anything that we talked about with thermodynamics between Monday and today? What are some words? What are some equations? What are some things that we know? Endo and exothermic. Okay, so what does endothermic mean? Good. So for endo, we're going to take in heat from the surroundings. What does it mean to be exothermic? Good, you're releasing heat. And is that going to the system or to the surroundings? Yep, to the surroundings. Okay. So for endothermic, you acquire energy, and then for exothermic, you release energy. Okay. So this is a lot of times where I start to say equal and opposite, if you haven't heard that before or had heard me say that before. But if something is taking in heat from the surroundings, something had to give it off in order for that thing to take it in, right? So something's releasing as another thing is taking in, and same thing. Something is taking in what the other is releasing. Okay, so that's equal and opposite between them. That's what we kind of think about when we think about calorimetry, right? As the copper that we talked about today was releasing heat, that's what was being taken up by the water. Okay, so the copper is releasing energy, and then the water is taking that heat in. Okay. What else do we know about thermodynamics?
No. Sorry. It's divided by.
We have the loss of
Yep, we have the laws. Do you know what those are?
like the energy, it's like constant.
Right. So the energy of the energy of the universe is constant. So again, that's where this kind of comes into play, right? If the energy of the universe is constant, if something is releasing heat, something has to be taking that in. That's going to be the same. What's another word we use? Heat, energy. There's another one we talked about.
Temperature, they're different, right?
Yes, because when we talk about, so one equation is Q is equal to MC delta T. right? Q here is going to be your heat, but T is your temperature. So this Q is heat. This T is change in temperature. What's the M and C of this formula? Good. Does anyone know what our units usually are for mass? Mhm. And then this is going to be your specific heat. Constant. And this is going to be in joules per grams times degrees Celsius. Okay, what questions do we have about Q is equal to MC delta T?
Question I had, I remember like today, during one of the examples, she had like this number she put in, which was like 4.1 something.
Mhm.
Is that like the constant?
So when we talk about Q is equal to MC delta T, this C constant here, this specific heat will be specific, for lack of a better word, for that specific material that you're using at that phase. So when we talk about 4.184 or 4.814, whatever that is, I think it's 18. This is your specific heat for water. So that's liquid, right? The phase of liquid. When you have gas, I believe it's like 0.9 or something. It's less than 1. And then when you have solid, that's 2, right? So depending on the phase, depending on the substance, it will change. Water has a very high specific heat, and so that's why it requires so much energy for you to change temperature. While your metals like copper or aluminum, something like that, they will have a lower specific heat, so it'll be easier for it to change temperature. Yes.
Will they give the constants on like the quiz, tests or exams, if it were just to be water, would we have to know water's constant temperature?
I believe it should be given to you. The only time it won't be given to you, I believe, is if you have to solve for it, obviously. But yeah, I don't think you're required to memorize this. I think it should be in all the questions that you have. I don't know if that's true for your homeworks because you have like the internet available to you. But for any quizzes, you shouldn't have to look up a specific heat if it's needed to solve the question. Okay, what other questions do you have about that? This equation? How do we do change in temperature? Is that T? Good. So change in temperature is always going to be T final minus T initial is equal to delta T. Okay, so sometimes you might have a negative temperature or a negative temperature change. So what does that make your Q if it's a negative temperature change?
That makes it exothermic or release it.
Awesome, right? So if we have a negative Q, that means we have negative energy. We have negative energy, we have less energy at the end than we do at the beginning. We have less energy at the end than we do at the beginning, that means we have an exothermic reaction. So we have a negative Q, something else has to be taken in that heat that has a positive Q. Okay, what's going to be the I didn't tell what units this is going to be in for your heat. That's going to be in joules. Yep. Okay, so our energy and heat are going to be synonymous, but temperature is different from heat.
Yeah.
After that whole question started, so let's just make sure we get back to that. What else do we have? What else do we know about thermodynamics? State function? Yeah, awesome, right? So what does it mean to be a state function? Awesome. Right, so for state functions, we only care about the initial and final, I guess we'll call them positions. of the, we'll say thing, whether that be system or surroundings. Right, so it doesn't matter if we're trying to get from, we'll say, trying to get from A to B. It only matters on this line. Oop, that's not very straight. Only matters on that line. Okay, whether you take this path to get there, whether you take that path to get there, or whether you take that path to get there, your energy difference between all of those will be the same. Okay, does that make sense of why state function is a state function? Okay, so we only care about final and initial, right? It doesn't matter what our temperature changes along the way, as long as we just have the final temperature and the initial temperature. When we start from like exo or endothermic, it doesn't matter where we start or where we end, as long as we just see the difference between the two. We don't care about the path in between. Any questions about state functions? Okay, what else do we know about thermodynamics?
The change of energy is heat plus work.
Awesome. So we know that the change of energy is going to be delta E is equal to Q plus W. And this is going to be your heat plus your work. And we should note that this is the change of internal energy. Of the system. Okay, so this is where Q plus work, heat and work is where we start talking about the system and the surroundings a little bit more, right? Heat going into the system, heat coming out of the system, work going into the system, work being done by the system. Okay. So let's talk about a little bit of talk about a couple examples for this one. So we have a box. Okay, I always like to think of this one as, right, I work out, I go to the gym. I like to think of this kind of in that sense. So if you have a box or you have a person going to the gym, if you are lifting weights, running on the treadmill, doing whatever you do, are you doing work? Or is work being done on you? You are doing work, right? If you're actively exercising, you are doing work. So if you are the system, is work being done on the system or by the system? It's being done by the system. So are we having negative work or positive work? It would be negative, right? So if I look at my ability to do work before and after my workout, I just worked out. I have less work available to me. Work was done by the system. I have now lost work. Does that make sense? Right, so work done is a negative W. Right, if you are working out, you are doing work. The system is doing work. You are losing work because you're actively doing it. Okay, what questions do we have about that one? Does it make sense? Makes sense. Okay. Okay, so while we're working out, I start sweating. Am I losing heat or gaining heat? I'm losing heat, right? If I'm actively sweating, I'm losing heat. So if work is done, or I guess we're losing heat by system. I didn't spell that correctly. We're having a negative or positive Q. Negative Q, right? If the system is losing heat, we have less heat available.
Oh,
And so we are losing that to the surroundings. Okay, so let's say I work out, I now have less work. I go home and I fall asleep. What is, right? So if I fall asleep, when I wake up, do I have more work or less work available to me than immediately after working out? I have more work available. So work was done on me to give me more work. So work done on the system, push this way. It's going to be a positive or W, or positive or negative W. Positive W. Right, and then I was just sweating, my sweat dries, I get cold, I put a blanket on. Am I gaining heat or losing heat? I'm gaining heat, right? So the system gains heat from the surroundings. Is that going to be a positive or negative Q? Positive Q. Okay, does this make sense in terms of what's the negative W, positive W, losing heat, gaining heat? Okay, this is very similar if you think of Q as in like an endo or exothermic reaction, right? If you're losing heat, it's going to be exothermic, it'll be always negative. If you're gaining heat, that's a positive Q. Positive energy has to be absorbed, and so that's going to be positive and endothermic Q. Okay, if the system is actively doing work, they are losing work because they're actively doing it, right? But if work is being done on them, that's a positive W. All right, if you get your hair done or your haircut, right, work was done on you, you now have more work.
how do you determine what's the system and what's the surrounding?
They will usually tell you what the system and the surrounding is. Or they'll like emphasize like considering this is the system. But when we start talking about chemical reactions, your molecules will be your system. Everything else will be your surroundings. So if we talk about like water dissolving, or sodium chloride dissolving, we'll say, right? If we have a beaker, we have our sodium chloride. I guess we'll have Na and Cl, right? We have our sodium chloride. This is your system. If you have water, it becomes sodium plus and Cl minus. These two are going to be your system. Your water is your surroundings. What other questions do we have about work, heat, system, surroundings? Does that clarify it a little bit? Yeah, feel a little bit better. Okay, what else can you tell me about thermodynamics?
The thermal equilibrium.
Yeah, so we have thermal equilibrium. And when do we get thermal equilibrium? What type of problems? When do we reach the same temperature for things? Say that again. It doesn't necessarily have to be room temperature. We did a couple examples today where we reached the final temperature. What are those problems called?
Kind
of. I'm looking for a different word.
The calories.
Yeah, the calorimetry, right. So when we have calorimetry or calorimetry problems, that's where we reach that thermal equilibrium, where they come to the same temperature, or that same final temperature between the two of them. So you have something at two different heats. They will eventually meet between them. They will not meet in the middle because if it's two different materials, right? One could be water, one could be a metal. Water is going to take a lot more energy to heat up rather than the metal is to cool down. And so they'll reach a thermal equilibrium between the two of them. Okay, so that's awesome. We have thermal equilibrium, we have calorimetry. This is where that Q is equal to MC delta T equation comes in. This is where thermal equilibrium comes in.
Wait, so what again makes a thermal equilibrium?
So if we have two substances, so if we have, we'll call this A, and we'll call this B. Right? If A is at 92 degrees Celsius and has a specific heat of 0.914. And then B is at 24 degrees Celsius and has a specific heat of 2.14. C stands for specific heat. So that's this C question or that C term in there. Your Q is your like actual heat. Right, if these two substances, I can feel a sneeze coming, so if I sneeze, I apologize. So if these two substances come into contact, right, they're going to reach a thermal equilibrium where they will reach the same temperature or the same final temperature somewhere in between 24 and 92 degrees Celsius. Which one do you think will have the bigger temperature change? A. Why do you say A? I like your thought process, but there's a better answer.
Okay.
I agree that it's going to be A, but why is it going to be A? Yeah, so this specific heat is 0.914, while this specific heat is 2.14. So between these two, this one doesn't require a lot of energy to be put into it in order for it to have a temperature change. It will very easily heat up or it will very easily cool down. Okay, while B here needs a little bit more energy, needs a little bit more time. So this one will be able to change its temperature faster to 24 or closer to 24, then 24 will be able to change it closer to 92. So you would expect it to be a little bit closer to that 24 range rather than the 92 degrees Celsius.
So
Yes.
Like specific heat, like what is it kind of?
Yeah, so your specific heat is basically like how easy it is for a substance to heat up or cool down.
Okay.
Okay, so we were talking about water, right? Water has a specific heat of 4.184. So comparison to 0.914, this one is a lot higher than 0.914.
So it's gonna be like slower.
So it's going to be really slow, right? If you think about boiling water on a stove, it takes longer for your water to boil than it does for the pot to get hot.
Mhm.
Okay, that's because your water has a higher specific heat than the pot that it's made out of, whatever material that pot is made out of.
Mhm.
Okay, so right, that's why you don't touch the edges because it's going to be hotter than whatever the water is on the inside. Yes.
So would you consider the pot to be the surrounding?
Yes. Yep. So in that case, your water would be your system, while your everything else is your surroundings.
And is that why if you were to place like a bigger pot compared to like a smaller pot of water, the smaller one would have the place?
Yep. Right. Because if we looked at like, if we looked at Q is equal to MC delta T. If we're looking at this mass component, right, the same energy has to be required, or whatever energy it's required to heat that temperature up, that temperature change will be the same between your two pots, but one's going to be heavier, one's going to be more massive, requiring more energy.
Okay, one more thing.
Mhm.
So with the lower C, it's gonna take No, it's gonna go faster to get the Q?
Mhm.
Okay.
So we can actually solve this problem to see where the temperature would end up. Okay, so let's say we have A has a mass of, someone give me a number. 12.6 grams. And then B has a mass of, what'd you say? Okay. So A has a mass of 12.6 grams, B has a mass of 24.3 grams. We know what is this gonna be, our initial or final temperature? That'll be our initial, and then what are RCs again? Your constant, your specific heat. So how would we set up this question? How would we find how to solve this? What would we have to do?
Get the mass. Change the temperature.
Right, so what's gonna happen? Which one's hotter between the two? A is hotter. Is it going to get hotter or cool down?
Oh, wait, no, cool down.
It'll cool down, right? So A's temperature
Yeah.
is hot now and will go to cold. Right? It's gonna get colder. So is it gonna be releasing heat or gaining heat? It'll be releasing heat. So you're gonna have a negative Q or a positive Q for that one. It'll be a negative Q, right? A is gonna have a negative Q. What does that mean for B? It's gonna be equal and opposite, right? It'll be doing the exact same thing, just in the opposite direction. So instead of going from hot to cold, this will go from cold to hot. So any energy that this A is releasing, this B will gain as the positive energy, right? A is releasing heat so that B can gain it. So what can we do to our Q is equal to MC delta T?
So for the mass,
So you just do whatever Q you have is the other one. Are we solving for the final temperature or we're solving for Q?
We're solving for the final temperature.
Yeah, so you take the Q that you get from part A.
Mhm.
You plug in the max of B. and constant.
But can we solve for Q with the information given? Can we solve for the answer of Q,
Because you need the final and.
Yeah.
right? You would need the final and initial. So no, we can't. But we know that their final temperatures are going to be the same. So we can say that whatever Q that A is releasing, B is gaining. So we can say that negative Q is equal to Q. Right? The Q of A is equal to the Q of B. Q is equal to MC delta T. So we can say that negative the mass of A times the specific heat of A times delta T is going to be equal to the mass of B times the specific heat of B times the change in T. Right, whatever Q is being released by A is gaining the positive version of that B. What questions do we have so far?
so are we solving for the change? of T?
Yep, so we're basically gonna solve for the change of T to get that final temperature. So we can plug in T initial and T final. These ones where you have to solve for the final temperature are like the most math you have to do for calorimetry. Okay, so what can we plug in for mass of A? Good, so we can do 12.6 grams. What's our specific heat of A? 0.914. Does anyone remember the units? Okay, I can give it to you. Joules over grams times degrees Celsius. Yep. And how do we plug in delta T?
EF minus 92.
Awesome. Why'd you say 92?
That's the A's initial.
Awesome, right? We know that A is initially starting at 92 degrees Celsius. Change is always going to be T final minus T initial. We're initially starting at 92. We don't know our final, so we plug in TF. Does that make sense why we're doing that? Okay, right, we said that T final was going to be smaller than T initial. So this delta N or this delta T will be negative. This negative will cancel out that negative that we get here, and that'll equal whatever positive answer we have on the other side. So how are we going to solve up? How are we going to plug in the B side of this? So we had 24.3 grams.
The final temperature minus,
Awesome. Awesome. Any questions? Okay, so you can see that this can be a lot of math, right? So you have to multiply these together, distribute this, distribute that, multiply these together, distribute this, distribute that, all that fun stuff there. Do you want to go through that, or do you want to try that on your own later? Later? You want to go through it?
it's a.
We'll just go through them, right? You can combine these first and then distribute whatever that combination is to the TF and then to this one here. Again, same thing, you're gonna multiply these together, distribute this to here and distribute that to there. Yes,
With the joules over the G times the Celsius, how would that cancel out with the thing that you just are trying to put together with the grams?
good. So your grams and grams are gonna cancel out when you multiply them together, so you have joules over degrees Celsius.
Okay.
So then when you multiply by your temperatures, that degrees Celsius will cancel out.
So it's just.
So it should just end up in joules.
Oh,
Yep.
okay, gotcha.
Right, T files technically X, so your unit on 92 will just be joules, while your TF will be joules over degrees Celsius. And then later, when you're canceling everything out, and dividing and stuff, and your joules cancel out, you just have degrees Celsius. It'll be like joules divided by grams Celsius, so then it's flipped, and all that arithmetic. If you ever have any questions with the actual math, please don't hesitate to ask. I always mentioned I was a tutor in undergrad, and I felt like math was the hardest part for some of my students. So please just let me know if you have any questions. You know the chemistry, it's just the math that trips a lot of people up. Okay, any questions on this one? Does that help a little bit with calorimetry and stuff? Okay, awesome.
Is that like the hardest problem in elementary?
Pretty much, yeah. This is gonna be the hardest just because it's a lot of math. It's a lot of like, okay, what's being energy released, what's being energy absorbed, and setting it up correctly there. But just know that as long as you give something a negative and something a positive, your values will work out, right? If you ended up giving D your negative Q, you would have a negative Q on this side and a negative delta T on this side, so your negatives would end up canceling out anyways.
Can you go over the negative, like how A is negative Q?
So
Like, is that gonna be on every problem? Like, when do I know to do negative Q A equals Q?
So whenever you have, so basically any calorimetry problem, there will always be a negative Q and there'll always be a positive Q.
Okay.
Because something is your system that's either gaining or releasing heat. Let's say it's gaining heat. If your system's gaining heat, your surroundings has to be losing heat. But it's taking in energy from your surroundings into the system. Okay? Yes,
So if you accidentally make the wrong one negative, it'll work itself out.
it'll work itself out. Yeah,
Just one has to be negative.
just one has to be negative, one has to be positive.
Okay.
What other questions do we have? Feel good? Feel better? I think this is one of the hardest things, so if you have any more questions, let me know. Yes.
And how many questions will that be consistent, like on the exam?
So I would say for the exam, expect something similar to this, but probably not like a T final question. Maybe you're given T final and you're given T initial, but you have to solve for a specific key. Right, so you would just have one Q and you just need to find the specific key. Or I believe there's one more equation for Q, So you might just have to set like, might have to do joules divided by something to get your Q there, and then you can set that equal to whatever this is to get your specific. Does that make sense? Does that answer your question? Okay, let's go through this again. Maybe we just talked about all of that. Yep, so then in your slides from Monday, slide 23, that's when we talk about thermal equilibrium. She gives you something very similar when these are separated and then come together and find that middle ground between the two of them. So if you need to another refresher on that, that's where to look for there. Okay, and then I believe that wraps up all of Monday's material. So then we can go to today. We talked about more calorimetry, which is fine. And then we talked about a little bit of endo and exothermic reactions and stuff like that.
What does that mean, like the constant volume calorimetry and the constant pressure? Could you go over that? Or is that the same thing?
Pretty much, yeah.
Okay.
So like what we talked about today with constant pressure and constant volume and stuff.
Yes, yeah.
Yeah. So I still don't know how to spell calorimetry. It trips me up every time. So here we went through like a stepwise function for stuff in terms of how to solve it. So for constant pressure, we're just saying that nothing is changing, like the pressure's not changing, it's not an open system. And that's just basically keeping the volume the same and everything like that. So you can say that like your watt, so you have your calorimeter. That's a bad one. You have your calorimeter. Still bad, but you get the point. Then you have it insulated. It's a fun looking one. All right, so your heat is being absorbed by the calorimeter and you have your water in here. All right, so your water is changing by Q is equal to MC delta T. But it's being transferred to this like inflated portion of the calorimeter. And when you have that, they already take into account that mass component. Okay, so you just have a capital C instead. So you say your C calorimeter. So Q for this one is C calorimeter times delta T. The calorimeter will still go through a temperature change, but they take into account that mass component. So your C cal here, the units are joules per degree Celsius, right? Which is different from that C up here, which were joules times grams times degrees Celsius. All right, we see that difference between the two of them.
How will you know if it's mass is in it or not?
So you will have the units available to you, like they'll show, if they give you the C cal, you'll see that the units are just joules per degree Celsius. So it's taking out that mass component. Your units can be a very good roadmap to tell you what you have and what you don't have. So that's why I try to stress them enough. I passed physics because I kept track of units. I promise you they save you. Okay, and that's basically just constant pressure. It's just basically variations of this Q is equal to MC delta T relationship here.
Wait, so the two keys are equal to each other?
Yeah. So same thing here, right? This Q with the water, if it's releasing heat, would be negative, and that would be the positive Q of your calorimeter. Yep. Still same thing, equal opposite. One's releasing, one's gaining. In this case. Okay,
It's the same for constant volumes or the same.
yeah, pretty much the same thing. And again, she goes through that same like stepwise how to go through those type of equations if it's constant pressure versus constant volume. Okay, what other questions do we have on calorimetry? Does that feel a little bit better? Yeah, okay. Okay, so we talked about enthalpy a little bit. Does anyone remember what was defined, or how do you define enthalpy? Say that again?
Heat flow at a constant pressure.
Yeah, awesome. So enthalpy is your heat flow at constant pressure. Does anyone remember what the symbol for enthalpy is? Yep, delta H, capital H. Okay, you might see it as just an H, you might see it as a delta H, you might say it as an H with a dot or a knot, they call it. Or it might be on the left or the right. I don't remember. Either way, you'll see a knot, a little circle, looks like a degree symbol. That just means that constant at STP, so standard temperature and pressure. I believe you'll talk about that Monday. But in case you see that on a homework or something, that's what that means. Okay, so we talked about exothermic processes, and that's right when heat is released by the system to the surroundings, and then endothermic is heat absorbed by the system from the surroundings.
Like the examples of it.
Yeah, absolutely. Okay, so do you want to do like the three that she talked about in class and just kind of talk about that a little bit? Okay, so we did burning wood as our first example. And we'll draw a little picture, kind of think about it. Fire, great. Okay, so if we think about our little fire that we have here, this wood is burning. If we were standing here, what would we feel coming off of this fire?
Heat.
We would feel heat. So what is that system doing? It is
Releasing.
releasing heat, right? So if we are feeling the heat as the person. So the system of burning wood is exothermic, right? Heat is released.
How do we know that, like, I know she explained it today that it wasn't like the wood that was gaining heat. How do you know that would help with that?
I believe she'll make it a little bit more obvious what's your
Okay.
system and what's your surroundings. But I think for right now, if you like, if she said, okay, burning wood, that is okay, not the process of burning wood, but the actual burning wood is the system. Okay, right. So if you were to talk about the process of burning wood, what one would that be? That would be endothermic, right? You have to put heat in to burn it in order to allow that reaction to happen to release that heat. Okay, right. So you can kind of think of like the endothermic process is like putting the match on the burning on the wood, and then it releases the heat. Okay, does that make sense? Why it's an exothermic reaction? Okay. Okay, your next one was rain forming from gaseous water. Yep, so if we think of rain, what is rain?
It's falling in the sky.
I heard water. So we think it's water, it's definitely water, right? Would rain be in your products or reactants if we're thinking as a chemical reaction? It would be your products, right? So we're gonna say this is water. Is that what phase is water in? what do we usually call it? Liquid, yep. Right, rain's usually liquid. So look at our liquid phase. And it's saying it's going from gaseous water. So what would our reactants look like? Still gonna be H2O. What's our phase? Gas, yep. Okay, so if we're going from gas to liquid. Yep, that's that little graph you're talking about. Yep, so that's condensation. This phase change is condensation. And condensation is exothermic or endothermic? It is exothermic. Right, if we were trying to take something from liquid to gas, right, if you're boiling water, do you put it in the freezer or do you put it on the stove? You put it on the stove, right? You need to put heat in order to go from liquid to gas. So in order to go from gas to liquid, it's going to be equal and opposite. Whatever heat it gained to get to gas has to be released to get back to liquid. Okay. Tell me about chemical bonds. Does all we talked about this at the very end of class. Does bond formation require or release energy? Okay. So bond formation releases energy. So is that endo or exothermic? That's exothermic. Okay, so I kind of think of your phase changes as bond formation or bond breakage. Okay, so if we think of bond formation releases energy, what happens to bond breakage? Is that going to require or release energy? Good. Right, the opposite of bond formation is bond breakage. Is that going to release or gain energy?
I really gain.
Good, right? So formation is the opposite of breakage. So release, the opposite is required or gain, right? So bond breakage requires energy. Right, again, equal and opposite. Bond formation releases, bond breakage requires. So if this one's exothermic, what's this one going to be? Endothermic. Okay, so I kind of think of your gas or your phase changes as either bond formation or bond breakage, right? You're not really breaking any bonds because it's still H2O on both sides, right? You'll still have that hydrogen attached to the oxygen. But liquid is a little bit closer together than a gas would be, right? If we take all of the air in the room and then condense it down, we now form a liquid. That's kind of creating more of those intermolecular forces that we talked about. And if we're creating more bonds, we're forming more bonds, we have to release that energy. So your phase change going from gas to liquid or liquid to solid is always going to be exothermic and always will release energy. Okay, if we're trying to expand our gas, right, again, boiling water, we're trying to make it take up more space, we have to break those intermolecular forces, break those pseudo bonds, right, we talked about. That's going to require energy to go in order to break those bonds. Who did I lose there? What questions do you have about that? You okay? Yes? You're good?
If you were to relate like an enzyme, so like the bond breakage,
Mhm.
is that what? Once you start eating up, it just.
Right, so if you work with proteins or if you're like cooking food, right? You heat that up, your protein in there is going to heat up and the bonds that's in that protein disintegrate pretty much and make it lose its shape. You're breaking bonds that's holding those proteins in the shape that it needs to. And so when you heat it up, you are putting energy into those bonds, breaking them apart, and then it loses its shape and it loses its function. Great question. Or great relation too. I work with a specific enzyme all the time. We always keep it at 4 degrees, right? So we always keep our bonds together. So we always want to keep them cold. Okay. And then the last one we talked about was your body processing food. I can't remember if she said that this one was endo or exothermic. But if we're talking about the process of processing food, that would be require and or release energy. The process of processing food, it would require energy, right? But if we're just talking about your body processing food, it's not going to be endo or exothermic. Exothermic, right? So the process of processing requires energy. But your body actually processing that food will release energy. You'll have more energy available, right? That's if you're doing a marathon, you're running or something, you take those quick carbs so that you can use that energy to then be released and you can go to your muscles to keep going. Right, so this is exothermic as well. And that's pretty much where we wrapped up today, I believe, except for enthalpy diagrams. This is the last thing. Any questions on endo or exothermic processes before I move on?
Okay, so the ice cream one that she
Mhm.
said, like, can you explain that one in an endothermic way?
Mhm.
Or in an exothermic way, sorry.
Yep. So if we have an ice cube, she said ice cube melting.
I don't remember what she said, but like.
Okay. So if we take an ice cube, right, if this is in the freezer, is the freezer cold or hot? It's cold, right? So your ice cube, is this solid or liquid? This will be solid, right? So right now it's solid and at a cold temp. Okay, if we take this out of the freezer and you put it on your countertop, is your countertop going to be warmer or colder than your freezer? It'll be warmer, right? So we're going to put it in a warmer temp. If we're going from cold to warm, what's going to be our temperature change here? Negative or positive? Positive, because what do we do for temperature change? Final minus initial, right? So this might be at 25, this is going to be at 0. So your final minus initial will be a positive delta T. If we have a positive delta T, what does that mean for our Q? It'll also, right, Q will also be positive because you're gaining that energy. So if we go from solid to liquid, right, what is our ice cube going to do at room temperature? It'll melt, right? So if this goes to liquid, so we just get a puddle of water, is this going to be an exo or endothermic process? This will be an endothermic process. Good, the bonds are breaking and creating a puddle rather than an ice cube.
Is it because like the heat of not encountered?
Right, so when you get a cold beverage and you put ice in your beverage, your ice cube is getting hotter while your soda or water or whatever is getting colder from your ice, right? Like that's like your dynamic there.
But just depends on what it's at. Like,
Mhm.
what it's at.
Yep. And so it doesn't really matter the time it takes, whether you have a cold beverage or a room temp beverage, if you put ice in either one of those, it's not going to matter too much. Or one's not going to be like faster than the other. Your colder one will get to its colder temperature a little bit faster than if you had like lukewarm something. Right, that liquid is going to have a specific heat. It's going to have a temperature change it needs to get to that ice cube. So it'll eventually get to the same temperature anyways. That's also why you should wait a little bit after you add ice to drink your drink. It's not going to be immediate.
What does this have to do with energy? Like, difference in energy?
In like terms of endo or exothermic.
Yeah.
Yep. So your endothermic is the energy process. Okay. So we're saying that energy will be gained from the system to the surroundings. And so we're going to have a positive energy change in your ice cube melting here. So if we were to look at an energy diagram, we have our, I guess this would be like energy on this side. Where would we put our reactants in our products? Is reactants going to be lower or higher than your product? It'll be lower. And why is it going to be lower?
It's gaining.
Right, it's gaining energy. It's an endothermic process. So our energy is going to be higher in the system than it was when we started. So your reactants are down here. And we increase our energy to get to our products. Right, so this is our ice, and this is our puddle. Right, so in order to get from ice to water, you have to put energy in. Right, in order to get from water to gaseous water, we have to put it on the stove. You have to put energy in, put heat in order to get into that next phase. I mean, if you had water and you had to put it to ice, you put it in the freezer, you're going to lose energy and to get back to ice. And so this reverse process would be exothermic. Right? If this is endothermic, this process will be exothermic. Okay, what other questions do we have? We feel a little bit better about material from Monday and Wednesday? Yes? Okay. So it was 6 o'clock, so I can let you go if you have no more questions. If you have any questions all over the weekend, feel free to email me. I'm not doing anything, I'm just hanging out with the puppy.
I do have a question.
Yeah.
about chemical bonds. So like
Mhm.
this will pass like building last place.
Yeah.
So we have like IMF, we talk about IMF.
Yeah.
And all that. Is chemical bonds part of IMF?
So,
Or what is it? Okay,
yeah, so it has to do with like inter and intra molecular forces. So when we have inter, this means between molecules. And then intra is in within. Right, if you're doing intra-state shipping, right, you're staying within the state of Texas. If you're doing international, right, it's going to a different nation. So chemical bonds is going to be between two atoms. So that's like your single and double bonds between or triple bonds between the carbon and the nitrogen. This is a chemical bond that's happening. Is this bond polar? Why do you say yes? Good, it's asymmetrical. Nitrogen is going to be more or less exothermic than carbon. It goes carbon, nitrogen, oxygen, chlorine. It's going to be more more electronegative. Wow, I don't know my E words there. More electronegative than your carbon. So your dipole points this way. So if we had two carbon nitrogen bonds, right, both of them have that dipole. So you can have what kind of intermolecular forces between these two molecules? You have a dipole-dipole. This molecule has a dipole. This molecule has a dipole. And so your IMF here is dipole-dipole because they both already have a dipole established within their bond.
Can any of them be, like, I know that all have LDF,
Mhm.
but and some of them have ion induced or something induced dipole.
Yep, so you can
Do they all
have
that?
You can have ion-induced dipole or dipole-induced dipole. And basically that's, if you're inducing something, that means you have a non-polar molecule to begin with. So if we had our CN again, and then we had a non-polar substance like F, this could be a ion-induced, or not an ion, a dipole-induced dipole. Because we brought something that has a partial charge close to something that has no charge. And so this partial negative will attract a partial positive on this fluorine. So for the second that it's close, this side will be partially positive, this side will be partially negative. But if this goes away, then it returns back to its nonpolar state.
So any of them can have that, because it can happen to
Yep, it can happen to any of them, as long as whatever is being induced is already nonpolar, then it can have it. You need to have, in order to induce something, one of them has to be nonpolar. And then same thing if we brought like a sodium ion close to this fluorine, then this fully positive charge would attract the negatives from your fluorines over here. Yes.
What if you did an ion into a dipole, like the Na plus close to the Cn?
Good, so that's a great question. So you could do Na plus, and then you can have Cn. Which side is going to be your partial negative and which side is going to be your partial positive? Then
The Na is the positive?
Na is the positive, and then off of carbon and nitrogen, which one's going to have more positive side? Carbon's going to be more partially positive and more partially negative, right? So which one of these two is going to be attracted to this sodium? The nitrogen will be more attractive, right? So it'll flip it pretty much. So it's like, okay, sodium comes in, your nitrogen is going to flip to this side. So then your partial negatives on this side and partial positive is on this side. And let's say our usual dipole is like this. This extra positive charge is going to attract more of those negative charges. So now your dipole is like this, right? It has a stronger dipole, making more of your negative charge on that left or on that nitrogen side now. Does that make sense?
What is that called? Like ion induced dipole ion?
So this would just be ion dipole interaction. It would not be an inducing of anything because we already have established a dipole in our bond.
Oh, okay. It's just ion dipole.
This is just ion dipole. Yep, because we have an ion and we have a dipole already. It's just going to create a stronger dipole.
So now the dipole's pointing, it's the same thing, essentially it's still pointing towards.
Yep, still pointing towards nitrogen. It's just going to be more of those electrons are going to hang out by that nitrogen
Okay.
this time. A dipole is just the probability of where you're going to find the electrons. So now there's just a greater probability that they're going to be by the nitrogen. good questions all around.
That makes so much more sense now.
Mhm. Okay. Any other questions?
One more thing about the inter and intra.
Yeah.
Can you explain that?
A little bit more, yeah, so. When you're talking about like intra, that's like just saying we have a whole bunch of water molecules. What IMFs are those experiencing, right? We have. So talk about a whole bunch of water. Things, sometimes it's better with the visual, right? We have a whole bunch of water molecules. What kind of intermolecular forces can this one have? Yeah, because we have polar molecules.
Oh, yeah.
So we have dipole. Yep. We have LDF. And we also have hydrogen bonds, right? We have an oxygen attached to hydrogen, so we have hydrogen bonding as well. Okay. So intra is what these molecules have between each other. Inter is if we now said, okay, we have a hydrogen and we have a water molecule, and now we put it in together with some of that cyanide that we had, that CN. Thank you so much.
Very helpful.
Thank you. Have a great weekend. All right, now between these two molecules, what IMFs can we have? So this one's just dipole. And LDF. So intra is like within the same substance. This is between, inter is between the two.
Okay. So this one wouldn't have hydrogen bonding, the one with cyanide, because even though there's still oxygen available to be bonded, we're not bonding it with another hydrogen.
Right, we're looking at how this partial negative of the oxygen interacts. Like we're looking at how this partial positive is going to interact with this partial negative, and how this partial negative is going to interact with that partial
So
positive.
that was inter.
This is inter. Yep. So inter is between molecules. Intra is like within the same molecules. Anything else? Okay. Wrap it up there. If you do have anything, please just let me know. I'm happy to answer your questions at any time. And I will see you Monday.
Thank you so much.
Yeah, of course. Have a great night. I did resume record this, so I should be able to post it.